All right, so name to structure. What is the parent chain in this first one, and how many carbons should it have? Pentane and 5, yeah. All right, so we have 1, 2, 3, 4, 5. And dichloro, we know that di means 2, and chloro is just chlorine. And does it matter? Yeah, 2 chlorines. And so does it matter if we start from the left or if we start from the right? No, because either way you'll end up with a 1,4-dichloro. So I'll just go left to right. So 1, 2, 3, 4 dichloro, and that is it. All right, sec. Some people overthink the sec and tert. That really just means secondary and tertiary. It's just short for that. So we have a butyl that is also a. How many carbons would a butyl be? 4. All right, so we have butyl and sec for secondary, and we have a bromide as well. So somewhere here we need to place a secondary bromine, which would in turn make the butyl secondary. And this seems weird because this is actually saying that the butyl group is the substituent, but it, you'll see when it gets drawn out. So either way, secondary position, a secondary halide could go in either of these places. So I'm just gonna go ahead and pick one. So again, we see here that the butyl group is actually has a secondary bond to the bromine, and it's secondary because this carbon is bonded to 2 other carbons. So does that make sense? All right, cyclics. What will the parent chain of this molecule look like? A triangle, right? And after the methyls are drawn out, you'll see that it kind of looks like a bikini. And also because there's only 3 carbons to pick from, your 1 and 2 position can be ambiguous. You can put them wherever. And so I'm just going to pick the top positions. But also we have trans. And so in the trans position, we need our dimethyls to be pointing in opposite directions. And so what would you do in order to show that? Not necessarily pointing up or down, but yeah, Michaela, dash and wedge, because you prefer the dashes and wedges because it's in a cyclic, it's on a plane, kind of like this, and so one would be pointing down and one would be pointing up. So I'm just gonna pick them. Because either way, they all end up being dimethyl cyclopropane. And that's that. If it was cis, then it could be both wedged or it could be both dashed. Good? All right, so bicyclates. All right, so one of the first things that I would look at is what the bridge, what the bridge is supposed to look like. So the first number tells you the first 2 numbers are telling you how many carbons are on each side of the bridge. And drawing it out, it's almost like a bridge that you would go over if you were to drive over some water. So here we have 3 carbons on one side of the bridge, which you could draw looking like this. 1, 2, 3. 1 carbon on the other side of the bridge. 1 carbon here. So just to highlight carbons, 1, 2, 3. And on the other side of the bridge, we have 1 carbon. And the last number in the bracket simply indicates how many carbons lie on the bridge itself, which is 1, and I already drew. So does that make sense going from that name? All right, and if you were to go from this this structure to the name, we know that we start from what we call a bridge head. And, that should be somewhat intuitive, because a head of a bridge would be the end of it. And so the end of the bridge would be one of these. So I'm just going to pick the top one. And for bicyclettes that have a bridge like this, to go from this structure to the name, you would go the longest side first. So you would go this way, and it would be 1, 2, 3, 4, 5, 6, and the last carbon that you would name is always the one that is on the bridge itself, 7. And we get our hep. Good? All right. So we have another heptane, but something is different about this one. Can somebody tell me what they think it's going to look like? It's fused, right? So a 0 on the last number tells you that it's fused. So there's no carbon on the bridge that you're driving over, and so you're just going to have a line instead of a point, which would indicate carbon. So you're just having a line, and you have 3 carbons on one side, which you could draw looking like this. I'm just going to highlight them again. You have 1, 2, 3 carbons, and the other side has 2. And chloro. All right, so as usual, we start at a bridgehead. I'm just going to call this one. So again, we want to start with our bicyclettes. We go to the longest side first. And so we would start out going 1, 2, 3, and we don't need to keep going because we see where we're going to place our, actually, my bad, mistake. Your bridge carbon when naming will be your number 1 carbon. All right, so that's where you're always going to start. My bad. 1, 2, 3, 4, and I'm not going to keep going because we already see where we're going to place our chlorine, which would be in the 2nd position. All right, and that is that. Any questions? Okay, Eduardo, doesn't matter if you did it reversed. No, so I'm just gonna draw this one again. So you can also have the longest chain on the left side if you were to ambiguously draw it, and it would still be the same thing, because if you were to rotate it around its own axis, you would simply get that as well. No problem. All right, so your 2,2,1 heptane, you've probably seen 100 times. Going over chapter 4, it's your classic. So it kind of looks like a butterfly. So I would just get used to drawing it. here is your 2,2,1 heptane. So this will always be the structure that it will look like if you have a 2,2,1 heptane. Now, we know that you don't really have to go through the numbering process if you know that your last carbon will be the carbon on the bridge. And our last carbon, because it's a heptane, will be our 7th position, right? So we would have a methyl on the bridge. Make sense? Any questions on that? All right. And as you guys mentioned in another previous section mentioned, you guys are a little bit more comfortable going from the structure. And so to save you guys, the typing in the chat, here is our parent chain. And so where do we start from? The left side or the right side? The left side. Okay, so if I were to start from the right, 1, 2, 3, 4, our substituents would be 4 bromo and 6 chloro, which is of a higher number than if it were to be going from the left, which would be 3 and 5. You see how this adds up to less of a number than these. So that's why we prefer to go from the left starting out. So we have 1, 2, 3, 4, 5, 6, 7, 8. All right, so what's our parent chain? Octane. So we have an octane. All right, and we have a chlorine on the third. Chlorine on the third. We have a bromine on the 5th. And we have a methyl on the 6th. And so you would simply just put it together. And so we have halogens and a methyl group. So could somebody tell me, putting this together, what they think the name would be? Yeah, you guys kept in mind the alphabetical order. So you prioritized them, and that's how you're designating them by number. And you would alphabetically put them together. So it would be your 5 bromo, 3 chloro, 6 methyl octane. All right, so good on that one. All right, so we have a cyclo what for this one? Cyclopentane. All right, so how would we begin to look at this one? So we have 2 halogens, all right? And so 2 halogens, they both have the same priority, but what would come first? The bromine, because of alphabet. All right, so we could also call this the first carbon. And of course, we want the least numbers possible, so 2 and fluorine on the third. All right. And so we can say 1 bromo, 3, definitely not spelling this right, fluoro. So putting it together, it would look like bromo, 3, fluoro. Trying to keep up with the chat, but yes, you can also indicate that it would be trans. All right, so trans, that simply means your substituents that you're indicating are pointing in the opposite direction. And the reason why I didn't put a number for bromo is because sometimes if you have something on the first carbon, then you don't necessarily have to put 1. All right, so like, you know, if we had a methyl on the first carbon, like this bridge carbon, we would just say methyl bicyclo. All right. Would it be wrong to indicate the 1? Not necessarily. I'm just wanting to make sure that I touched on that because you could see it either way. All right. So just to go through the hassle of this one, this is your longest chain. And so if you guys wanted to count that up, I'm not going to make you do that, but it's a decane. So just going to clear up some space. So we have a decane. All right. And so looking at this one, you see we have methyl, methyl, and ethyl. It's 2 carbons. What would this one be called? Isopropyl. So let's just list them out so we don't get ourselves confused. We have a dimethyl, all right, because we have 2 methyls, dimethyl, and we indicate them with commas. So we have a methyl on the second and the third. We have a ethyl on the 1, 2, 3, 4, 5th, and a isopropyl 6, 7th on the 7th. And so in terms of alphabetical stuff, you would want to put them together in alphabetical order. So, but there's a caveat. So the prefixes that don't count, prefixes that don't follow the alphabet, are the things like di, tri, and so on. And secondary, tertiary. All right. So these don't follow the alphabet. So the things that you would be putting in alphabetical order are the ethyl, iso, and methyl. So can somebody tell me what the name of that would be? it's a long number to type down, so whatever. So E comes first, right? Again, using this caveat, right? Keep this in mind. These prefixes don't follow the alphabet, so I underlined what we're going to be looking at. 5, E comes first, ethyl. Then we have an I, comes before M. I'm definitely someone that'll, start singing my alphabet. Isopropyl.
Yeah, so iso follows the alphabet.
And dimethyl, 1, 2, 3. Dimethyl. All right. You guys did that one pretty good. All right, so just to make this one a little bit bigger. All right, so remember so we could make our bracket first, okay? So what would our bracket say for this one? So Jennifer, in this one, again, we're acting like the di. Again, I wrote it out before. Di, tri, things like that, and sec and tert don't count alphabetically. You just go to their what they're designating. So methyl, ethyl, and isopropyl are what we're considering to put in alphabetical order. That's why it came E, I, and then M. All right, so you guys are answering in the chat about the bracket. So of course we're going to start out with a bridge head, and we have 1, 2, 3 on one side, 1, 2, 3 on another side. All right, so it would be 3, 3, and there's only one carbon on the bridge itself, which would be 3, 3, 1. So you guys got that. So 3, 3, 1. All right, so which bridge carbon would you count as number 1 when naming? All right. Eduardo says the top one. Anybody else agree or disagree? Yeah, the top one, because it would be the closest to the substituent that you have. So this would be 1, 2, 3, 4, 5, 6, 7, 8, and lastly, our bridge 9. All right, so we see that from our total number of carbons, we have a bicyclo bracket non-name, no name, depending on where you're from. All right, and so we have a bromine on the second carbon, so it would be 2-bromo. All right, putting it together, see 2-bromo bicyclo bracket 3, 3, 1. No name. Questions? Everybody good on that? All right. And so before I move on, you may also see a spiro. You've probably seen it before in SI, but spiro, there's only 2 numbers. So for spiro rings or cyclics, there's only going to be 2 numbers in the bracket. Right? So you're often going to see it twisted like this. So just drawing an example. your twisted carbon will be your number 1. All right. And unlike your regular bicyclates, for spiros, you're going to the short side first. So that's the only one that you're going to have to remember to go to the short side first with, is the spiro. And so we'd go to the left first. So we'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so short side first, making the bracket. We have 3, 1, 2, 3, 4. Again, it's not a 0. It's not anything else. It's only 2 numbers in the bracket. And your parent would just be the total number of carbons. So, any questions on that? It was good. You're probably not going to see any more than maybe 1 or 2 spiros. Anyways. Why do you start on the shorter side? That's just, I didn't make up the rules. IUPAC, they came up with it over in England or whatever. So yeah, that's just, unfortunately IUPAC. But yes, Spiro, in comparison to your other bicyclates, Spiro is the only one that you start numbering on the short side. Stability. All right, these ones, this is where it sometimes gets tedious. So we have an ideal angle. All right, what is that ideal angle that we want for stability? (109.5), right? Our ideal angle is 109.5. So I'm not going to go ahead and rank these because you probably already did it already. The closest that you get to 109.5 is the more stable it will be. And so that doesn't mean the more carbons that you have, the better. Because even if you have a cyclohexane, if you start getting to 7 carbons, 8 carbons, and so on, you're becoming less and less stable again. So you want to get closer and closer to 109.5, which is your cyclohexane. The further out you go, regardless of the number of carbons, the further out you go, the more and more unstable you're getting. Make sense? And the reason for that is what? There's a term. Does anybody know? Not necessarily chair, but angle strain. There's a big amount of angle strain, and even, stress. So even if you were to, those that have a model kit, you could almost barely touch. You barely can make a triangle, and that's why these unstable angles readily break open in order to form a higher degree. But I don't even know that yet.
Eduardo, you have a point in the sense that if you just draw a planar cyclohexane, right, that's going to be 120. That's going to be so far away from that 109 that you're looking for. So that's why you do that chair conformation. So that chair stability gives you that 109.5 angle that you're looking for.
Yeah, so in order to touch on that chair, methyl cyclohexane, the chair of it will look like this. All right, some people draw it otherwise, but this is technically correct, in which you should be able to visualize it. It's kind of like a lawn chair, right? You're just chilling, right? called a chair. It's methyl, or not methyl, cyclohexane in general will be behaving in nature as a chair. That's because it creates the most stable bond angles. In order to get those more or less stable chairs from a given name, I personally would draw it out in 2D first. So we have a cyclohexane, we have a tert-butyl and a methyl group on a number 1 carbon. Right, so I'm just going to, you can ambiguously pick it. I'm just going to say this one. Here's our tert-butyl and a methyl. But what's the hybridization of that carbon? sp3. So something has to be wedged and something has to be dashed. All right? It has to be wedged, no matter what at the moment. And let's say the methyl's dashed. And so moving on to our chair. I'm just going to call this one our number 1 carbon because it's easy to visualize. And so one thing that I've always kept in mind is wedged is up, down is dashed. All right, down is dashed, 2 Ds. All right, so wedge is up, down is dashed. And so going from this drawing here to this one, we have an axial and equatorial position. And so if somebody knows, can somebody tell me at this carbon that I drew in blue what the axial position would look like? Pointing up, pointing down, diagonal. It would be up. And so which one of these would be pointing up? Using this rule of thumb, it would be our tert-butyl. And in the axial position would be our methyl. All right. And so what can happen is a chair flip, which really is just this point coming down and this point coming up. So it's like when you're a kid, you wanted to mess with your sibling or cousin, you drop their head down real quick when they're sitting in a chair, and you also bring the other side up, and you end up with just it flipped. All right, so this is now our first carbon because again, it just went to another conformation. So again, this is our first carbon. So why did we use wedges? Is because any carbon that's sp3 hybridized will have a 3D structure, and so all of its groups will be behaving in 3D, and you'd have to indicate that with wedges and dashes. And so if you when doing a chair flip, something that starts axial or something that starts equatorial will go to the opposite conformation when you do a chair flip. So an axial starting will end up in an equatorial if you do a chair flip. So this tert-butyl will now be what? If it was axial, it will now be what? Equatorial. Equatorial, and your methyl is axial. Can somebody tell me which one, if they know, is more stable? I'll just say A or B. And why? Can somebody tell me why? So yes, it would be B, or as someone else put it, number 2. It's because, yes, the larger group, it's not necessarily the atom itself. So, for example, it's not necessarily the atom itself, the atomic number. That's not necessarily the case in terms of stability. It's about the group itself. So there's this big electron cloud that takes up a lot of space in comparison to just this one. And the bigger the group, it is more stable in the equatorial position. All right.
Yeah. Just to add to that, so what Michael mentioned when about bulkiness and not atomic number. So if you had that methyl and a chlorine to compare on your structure, you would choose your methyl to be on the equatorial position and not your chlorine, even though your chlorine has a higher atomic number. And why your methyl? Your methyl is going to be bulkier. Remember, methyl is made of that carbon and those 3 hydrogens coming off of it. So what you're concerned with as far as equatorial and axial goes, you want to look at those electron clouds, right? So anything that is bulkier, has more groups, that's going to be the one that you prefer to have equatorial. Okay? So don't look at atomic number per se. In this case, look at bulkiness.
All right, and before we go to the Newman, here's another chair example. Again, just start with your planar. And I'm just going to say this top carbons are first. So we have a tert-butyl. And we have a third methyl. And they're both cis. So you could say they're both wedged. There we go. They're both cis, so they both have to be pointing in the same direction, in which you could make them do that with wedge. All right, so wedge is up, down is dashed. And so when going from this to your chair, again, just saying that this is the first carbon. We have a tert-butyl. Again, wedge is up, down is dashed. Wedge is up. They're both wedged, so they're going to be both pointing in the up position. If this is our first carbon, this would be our third. Now you could say if they are in the axial or equatorial position, and what would they be in? Both are axial, right? So the axial positions, it's kind of like anywhere where there's a elbow. So say the elbow's pointing up, the axial position will be pointing directly up with it. If the elbow is pointing down, then the axial position will be directly down. Right? Does that make sense? So this elbow here, it's pointing up, so the axial position for that carbon would be vertically up. The axial, this carbon, the elbow for it is pointing down, so the axial position would be vertically down. Does that help at all? An equatorial is diagonal, so any group that's in a diagonal position is equatorial. So in this case, it would look like this on that carbon. And if axial is down, equatorial is up. All right. So it kind of goes from back and forth between one carbon and another. So axial on this carbon is up, axial on this carbon is down, next one is up, next one is down. All right.
Yeah, and as far as wedges and dashes go, remember guys, when we have wedges and dashes on our plane structure, when we draw our chair conformation, the wedges and dashes don't tell us anything about axial or equatorial. All the wedges and dashes tell us is whether the group is going up or down. Because as you notice, axial and equatorial are interchangeable, right? Sometimes axial is up, sometimes equatorial is up. So if you see a wedge there, don't just assume it's axial or equatorial. Assume it's up, and then you follow the trend of the molecule like Michael drew it, and you're going to find their relationship in terms of axial and equatorial.
Yeah, and a perfect example of that clause is with this other example. So I'm just going to create some more space. And so in trans, it would simply be one is wedged and another is dashed. So now neither of them, now not both of them, but one of them will be pointing up and another will be pointing down. All right, so going to our chair. Again, just saying this top right one is our first carbon. Wedged, it's up, so we're just going to draw it pointing up. And our third methyl is pointing down. All right, remember our elbow positions. If your carbon has an elbow that's pointing up, axial directly from it is pointing vertically up. And similarly, if your elbow is pointing down, then axial will be vertically pointing down. So now you could say, after you drew it based on your wedges and dash, up, wedged, down, dashed, now you could say which one of them are axial and which one is equatorial. So can you tell me? Robert, no, not necessarily, because the name is just indicating that they're pointing in an opposite direction. The name isn't telling us which one is wedged and which one is dashed. You'll see that more in chapter 5. The tert butyl as axial, yes. And so if we were to do a chair flip, this one comes down, this one comes up. So now our first carbon is here. If this was axial, now it's what? With the chair flip. Our third carbon would be here. If this methyl was equatorial, it would now be axial. So which one of these, A or B, would be more stable? B. Yep. All right, so returning to Newman. So let's draw a 2, 3. All right, what's the hybridization of our 2 and 3 carbon? sp3, so we could draw them as wedges and dashes. So I'm just going to do both wedged for this example, and we have an implied hydrogen in the opposite direction. All right, and so how did you choose which carbon to put the substituents on the last one? Do you mean with this, Mackenzie? So I always like to go from bond line to a Newman. That just makes it easiest for me. And so there's a rule of thumb that I like to use. Anything that's in the directly up and down is on the plane. Things that are on the right are wedged, or vice versa. Things that are on the left are dashed, or vice versa. So when we draw our Newman, here's our front carbon. We have this methyl pointing down. What would go on the right? Again, this front carbon. Again, here's your rule of thumb. Yep, the methyl. So you have your CH3 and your hydrogen. Your back carbon, which is always with a bigger circle. The methyl, again, looking down this bond. The methyl is pointing up. CH3. And using our rule of thumb, our other methyl is on the right and our hydrogen is on the left. So any given bond line structure, you can use this to go to its Newman for that bond line. But we know that because it's a single bond, you can rotate around this bond. And so what will happen is that you can have these 60-degree rotations, and these give you different projections. And so here is this molecule, all right? It's the same molecule that I showed you before. But what it's saying is that this front carbon or the back carbon can rotate off of that bond, all right? And so in terms of stability, let me add our dimethyl. In terms of stability, all right, if you have, so right now, let me see, our structure would be like this. So you have a staggered, if like the moon and the sun, all right, if there isn't anything in line with each other, then we call it staggered, all right? And so if we are going to rotate, right now you have two of the biggest groups between the front carbon and the back carbon. There's only one bond rotation from it being eclipsed, from this carbon and this carbon being in line with each other. And so what we call that is gauche. All right, so one bond rotation away, one 60-degree rotation from being eclipsed with each other. And if they are eclipsed, they will be in line. All right, and so let's see. I were to rotate, so right now you see here, if I were to rotate and we have the front carbon methyl and we have the back carbon methyl in line with each other, they are eclipsing each other here. All right, so like the moon and the sun, this, and also if you were to look at it from another perspective, these hydrogens, these electron clouds are interacting with each other and creating a stress. And that's why eclipsed is much less stable than gauche and staggered. So eclipse is the same as gauche? No. Eclipsed is if you have your back carbon groups in line with your front carbon groups. So a better example drawing of this, we have the front carbon group here and the back carbon group here are in line with each other. That's eclipsed. But whether or not it's partially eclipsed is another story. So if you have partial eclipse and fully eclipsed, the difference between those is whether or not your biggest groups or not is eclipsing each other. So if you have a back carbon with a CH3 and you have a front carbon with a CH3, whether it be terbutyl, CH3, whatever it may be, your biggest groups, if you have the biggest group on your front carbon and you have the biggest group on the back carbon, if they are eclipsing each other, then they are fully eclipsed. The biggest groups fully eclipsed. If you have something like one of your biggest groups is eclipsing a smaller group, like a hydrogen eclipsing a methyl, then it's partial eclipse. Partial because it's not your biggest groups eclipsing each other. Fully is your biggest ones eclipsing each other. Does everybody get that? So in terms of stability, staggered we often called anti. It's your most stable. Then we have gauche. Well, actually, yeah, we have gauche. We have your partial eclipse and full eclipse. All right, so your eclipsing groups, your eclipsing conformation will always be the less stable of the others. So I'm just going to say A, B, C, D. So in graph form, which you may see on the exam, this is going to buffer now. So your, of course, most stable energy is this way, potential energy. Your most stable would be the one with the least energy, A. Next we would have B. These would be your partial eclipsed and your full eclipsed. All right. So again, the gauche, the difference between staggered and gauche. Number 3 here, I'm kind of answering this question for you guys, but your biggest groups are your furthest away from each other in this moving projection. Therefore, it's gauche. Therefore, it's staggered, right? And otherwise known as anti. All right. Opposite, your biggest groups are entirely 180 degrees across from each other. If you have your biggest groups only one bond rotation away, which would be 60 degrees, it would be known as gauche. All right. If you have your biggest groups that are in line with each other, your biggest groups, again, are fully eclipsed. And there's not one here, but a partial eclipse would look All right, so you have an eclipse, but it's not your biggest groups eclipsing each other. It's a minor group with an H and a bigger group with a CH3. That's why it's a partial eclipse and not a full eclipse. That's the only difference. All right, so does Newman projection make a little bit more sense? And Robert, yes. In these options, the 1 and 4 options would be gauche as well. So is there any confusion on this so far, or did that clear some things up? All right, so I know we're going over time, and so if you need to go, you can. But I'm also going to go over a type of reaction that you guys may see. But before you guys exit, as I mentioned before, please give me some feedback with the link that I just sent in the chat. I do want to help you guys as much as possible, so definitely give me some feedback before you guys head out. I sent the link in the chat. But yes, we can go over this quickly. So hydrogenation is applying hydrogens. All right. So
yeah, Michael, I don't think your links work. Like when you put them in the chat.
There we go.
Worst comes to worst. Oh, there you go. Perfect.
So hydrogenation is going from a triple bond or a double bond to a single bond. All right. So you're going from less bonds. You're going from more bonds to less bonds. You're going from more bonds to less bonds in hydrogenation. So say a double bond, if you add something like H2 or PT, then you would end up with a double bond. A single bond. That is as much as you guys need to worry about for hydrogenation. Think of it as you're hydrating something. You're adding hydrogen to it, all right? So if you're adding hydrogens to it, you're going from more to less bonds, right? So unfortunately, I do have to go. I have a section that I'm late for at 11. But Urta, I did make her and give her access to this. But the answer for this one wouldn't be, it would be it's not. Right, so I do have to go.
Go, Michael.
Those that are here, again, please give me some feedback with the link I sent in the chat. I posted it on one of the discussions as well. So definitely give me some feedback. But again, Urta will be here if you do have any more questions.
Thanks, Michael. Good luck.
No problem. Thanks.